Hello everyone, my name is Rhiannon Garrard. I am the new physical scientist here at Bryce Canyon National Park, otherwise known as the top step of the Grand Staircase. A big priority for the park this year is planning for the effects climate change will have on our water systems. And at Bryce Canyon, groundwater is the primary water source, both for our drinking water and for our ecosystems. And as climate change advances, groundwater is becoming more important everywhere, even in places with abundant surface water, because surface water is becoming less reliable, like Powell. Unfortunately, we can't walk up and touch or see or measure groundwater nearly as easily or inexpensively as we can with surface water. Plus, it moves very slowly, which means that negative impacts can be easily missed for decades or even centuries, at which point it's too late to mitigate or repair the damage. And then add on top of all of that the potential complications of climate change. And it's very easy as a community to feel daunted and deprioritize safeguarding the groundwater supply. Fortunately, however, the general effects of climate change at Bryce Canyon are in sync with the state of Utah as a whole. So today I'll be using data from Bryce Canyon to provide examples that are applicable to the larger region. And it's my goal to explain climate change predictions as simply as possible and to show you how these predictions relate to groundwater supply. So hopefully we can communicate about this a little easier and work together to protect the resource. And I want you to start by thinking about groundwater as like the stock market. If you use water, you have a stock in this market. How then do you protect your stock? Well, let's start with a budget. The groundwater budget is relatively simple. We need to balance recharge, which is how much water goes into the ground, with water loss, what is taken out of the ground. Rainwater tends to channel and run off quickly, so it's not a great recharge source. Whereas a good snowpack tends to sit and slowly absorb into the ground. For that reason, snow is by far the biggest recharge source in Utah. Maintaining a heavy seasonal snowpack is the best way to maintain a strong groundwater supply. But then, of course, this must be balanced by how much groundwater is lost. Water is lost from evapotranspiration, and that includes evaporation, where the air is drier than the land, and so the water is pulled up out of the ground. Then you have transpiration, which happens when plants breathe. Water collects at the roots and is released up through the leaves. Discharge includes groundwater loss to streams, springs, plus the one factor we have complete control over, well pumping. Well pumping provides drinking water for humans and livestock, as well as water for fire suppression purposes. So now that we know what the budget is and how to balance it, let's look at some of the climate change predictions and how they might impact this equation. First is the big one, temperature. On the left side here is the IPCC, or International Panel for Climate Change, their predictions. Out of all the sources I have found, they use the most up-to-date models. And they cover regions, and the graphs I'll be showing you are all from the Western North American region. And I realize the axes here are too small to see, but essentially the horizontal axis spans from the years 1900 to 2100. Today, the year 2024 is at the beginning of this gray box, which spans to the near future, the year 2040. Then on the vertical axis, all the graphs I'll be showing you start at 0. That's the historical average. From there, the average will either increase or decrease. And we see here that temperature is expected to increase quite dramatically, and there's a pretty high confidence in that. The graph on the right is the actual historical trend at Bryce Canyon. The average yearly temperature has increased here about 1 degree Celsius in the last century. Utah as a whole has increased almost 2 degrees Celsius in that time. But we have to be careful now about applying this to our groundwater budget. It's easy to imagine that higher temperatures will affect the entire budget. However, that would be making assumptions, and it's best to get as specific as possible to the variables on the budget to know for sure what effect they will have. And based only on temperature, what we know for sure is that increasing temperature is directly related to increasing wildfire risk in the Southwest. And so more fires mean more well pumping, and that's going to increase our discharge. Now, the majority of climate change projections involve precipitation. It's easy to make assumptions about how precipitation will impact the water supply. But in general, precipitation projections are not very helpful for the groundwater budget. Why? Well, the temperature prediction has high certainty. Precipitation is more complicated. Water vapor stays in the atmosphere an average of 9 hours, and then it cartwheels away. So because it moves so fast, it's difficult to predict the weather day by day, let alone make global century-long predictions. One possibility is that the equator will become drier, but the mid-latitudes where we are will actually become wetter. And that's why we can't make assumptions based on temperature alone. Another possibility is that there will be more extreme weather events, more long-lived rainstorms, and more longer periods of dry days. But these possibilities are not certain, and as you can see, the trends are not strong. They don't lean heavily up or down. And in fact, precipitation is leaning slightly up, but the historical record on the right is showing that precipitation has decreased at Bryce Canyon over the last century, and this is true for Utah as a whole as well. But at the same time, droughts have not increased in Utah. All the major droughts that Utah has experienced have followed the El Niño cycle, and while that's useful for climate purposes, it doesn't actually help us manage our water budget. To keep the groundwater supply safe really requires taking local measurements that directly impact the budget's variables: snow recharge, evaporation, and discharge. Anything less is making assumptions, and you wouldn't want to do that with your own bank account, so it's not really something that we should be doing with the groundwater supply. Fortunately, climate change predictions do include snowfall that can be used directly in our budget. Unfortunately, those predictions show snowfall decreasing rather dramatically regionally. There's pretty high confidence in this. On the right, we see Bryce Canyon's average snow depth in inches recorded over the last several decades, the most recent decade being the solid red line, all others being dashed lines. And overall, this last decade does not look so different, except for the months from March to May. The springs have been drier, and this is a trend that all of Utah is seeing. Drier springs mean that there's less time for the snow to join the groundwater supply. What does this mean for the future? Like the stock market, it's hard to say, but what does it mean right now? It means it's more important than ever to continue boots on the ground monitoring so that we know our current budget and we're ready to adapt accordingly. Moving to water loss, the real hole in our boat, so to speak, is evapotranspiration. Without evapotranspiration data, the groundwater budget is pretty much useless. You can put pennies in a piggy bank all day long, but if you don't know that there's a hole in your piggy bank, you're not really saving any money, are you? The trouble is, because we can't reliably predict precipitation, we don't know how much moisture is going to be in the air. Will there be more moisture? Will there be less moisture? That's going to impact the amount of evaporation. Predicting transpiration depends on knowing how plants will respond to climate change. Plants breathe less when there's more carbon dioxide in the atmosphere. If they breathe less, they transpire less, which means less water is lost. But that's assuming that the same species and number of plants remain in the area as the climate changes. Because of all these uncertainties, the IPCC, or really any models, don't predict evapotranspiration. I believe they did in the past, but the effect is really going to be incredibly specific to the local ecosystem. And we do not have a historical record of evapotranspiration at Bryce Canyon. It's not been a standard practice here or really anywhere. There are methods available, and I do list some helpful references at the end of the talk that are a great starting point. And I really believe developing evapotranspiration monitoring procedures is a crucial step for managing climate change. And I really encourage that if you have the ability to make it a standard practice. The last variable, discharge, this is really where human ingenuity makes the biggest impact. Discharge includes water loss through wells and springs. Water loss through wells is something that we can mitigate through water conservation practices. This graph here is based on groundwater reports at Bryce Canyon since 1957. The orange color being the number of visitors to the park, and that number has increased pretty significantly. Water use in blue has, of course, also increased, but as you can see, the park has gotten much better at conserving it since the 1950s. And really, since 1926, Bryce Canyon has received its water supply from the same shallow well filled. If necessary, there is more water available from deeper sources, but that is something we want to avoid doing or tapping into for as long as possible. Then, of course, mitigating and limiting fire risk is also a big part of conservation in this regard. As for springs, undiscovered springs are definitely a source of unintended loss. In 2022, a spring survey was conducted in the park, which tripled the amount of known springs in Bryce Canyon's inventory. And of course, there are probably many more that we still don't know about. But only a few of these are year-round and have any significant amount of discharge. And it's really not necessary to monitor every single spring because well pumping far exceeds spring discharge. So ultimately, it's more important to keep track of well water depletion. However, if a well is capturing water from new pockets inside the aquifer, the water level inside the well will appear less depleted than it actually is. And so tracking water loss in the aquifer through spring discharge is really an important way to catch if any well capturing is happening. Now, here at Bryce Canyon specifically, there are two additional sources of discharge that need to be addressed. The first is the Ruby's Inn thrust fault. These images here show a rough diagram of Bryce Canyon's aquifer system from a side view here and a top view here. So most snow falls on the southern edge of the Paunsaugunt Plateau and then travels down to the north, where it hits the thrust fault shown in red here. Now, fault lines have the ability to either block or channel groundwater flow. If the fault is channeling groundwater flow, then that means the water can freely pass to the north end of the aquifer, and the aquifer is much larger. However, if the fault stops the groundwater flow, then the aquifer is restricted to the south end of the plateau, and any private wells on the south end have the potential to capture from Bryce Canyon's water supply. Therefore, knowing the effect of the thrust fault is vital for the park. Now, Bryce Canyon's second challenge stems from the fact that the Claron Formation, shown in the peach color here, is made of limestone. Limestone can dissolve in warm weather, especially if the rain is high in carbon dioxide, which acts as an acid. If the limestone dissolves, caves and conduits can form both above and below ground. Geologically, this is called karst. The Claron Formation on the neighboring Markagant Plateau, where Cedar Breaks National Monument is, has karst in its Claron Formation, but so far none has been detected here on the Paunsaugunt Plateau. But this is really something that the park really must watch out for, because if a cave or even a small series of pipes forms underground, they can completely collapse or rearrange the aquifer. To use the stock market analogy, the effect would be equivalent to a stock market crash. Fortunately, though, the rest of the Grand Staircase does not have this problem. except for the very bottom. The Kaibab limestone, which caps the Grand Canyon, is the only other limestone layer in the region. So to summarize, climate change models have some use for safeguarding the groundwater supply, but don't get overwhelmed by them. It's far more important to maintain a local groundwater budget through measuring snowfall, evapotranspiration, improving conservation methods, minimizing fire risk, and monitoring well capture by recording spring levels. With that in mind, the priorities here at Bryce Canyon for our groundwater supply are to first understand the effect of the rubies and thrust fault. Our budget is only good if we know the size of our aquifer or the size of our piggy bank. So we're working on testing that fault line. The next priority to be worked on is to complete the groundwater budget by adding spring monitoring and evapotranspiration measurements to our list of data sources. And then the final priority is to mitigate any risks. Wildfire and contamination risk both increase with temperature. Then because our aquifer is housed in limestone, here at Bryce Canyon, we also really need to develop a plan to identify areas that may lead to karst development and really check up on those areas in the future with climate shifts. And that is the current groundwater situation here at Bryce Canyon. Here are some references covering the information I shared today. Thank you for listening.